There we are. We've arrived at part 11 of Nutrition and Metabolism, page 924. And as you can see here, we have yet another cell out here. This would represent the cytoplasm out here. And we get the glycolytic pathway or glycolysis, glucose breaking down to pyruvate. Here we have the mitochondrion. There's more detail to this little unit, so you can read about this at your leisure. So in the glycolytic pathway, we're going to pyruvate. We're getting a net 2 ATPs from substrate metabolism. Over here, we spin the Krebs cycle twice, and as a result, we're going to get 2 more ATPs. Okay, and then over here, we're going to do oxidative phosphorylation. We're going to get, no matter what they say, because they're considering other reactions and they're considering membrane crossing, which requires energy. I'm not going to do that. I'm going to tell you what you need to know for the board exam in medical school and nursing school is 34 ATPs right here. 34 plus those two give you a total of 38. If we were in a test tube and we had all of the proper reagents, then in fact we would get 38 ATPs because we wouldn't worry about the activities of the organelle. Here's an interesting little unit right here. We're going to produce glycogen. So the first thing you do when you eat food and you have adequate calories is you utilize the glucose from the food to power the cells currently needing energy in your body. That's the first thing that happens. You might be feeling a little peaked. You have some food and you feel better. The next thing that happens with any calories beyond your immediate need is you produce glycogen. After glycogen, you produce fat. But how much glycogen do you produce? You produce the amount that you need for 1 day. Where does it go? It goes to the liver. It goes to all of the muscles of the body. It actually also goes to the kidney, but the kidney only serves itself. Okay, so the liver actually is the one who collects all of this material here, this energetic material, and very carefully, how shall I say, deals it out to the body as it is needed throughout the day. Hopefully you're not stressing. If you just sprint around everywhere, you'll go through your glycogen in no time at all. And you'll hit the wall, you'll get tired, and you'll feel like sitting down or even going to sleep. Okay, so here we have glucose up here, blood glucose from having eaten food. We come down, we store the glycogen. The blood glucose goes down, we come back up, we release the glucose from the glycogen. We have the amount of glycogen that we need for a 24-hour day. How do we know? It's because it's based on the experience of the last 2 months, anywhere from 6 to maybe 10 weeks. If you have been running every day for the past year, because you're a distance athlete and you have 8-mile-a-day workouts or 10-mile-a-day workouts, whatever they are, then in fact you'll be storing exactly the right amount of glycogen that you need for your day-to-day, and your body knows it. Okay. Also, if you have hyperglycemia, you have a lot of glucose in the blood because you're somebody who has a, how shall I say, a candy fetish, then in fact you might, and unless you go running every day, you might have consistent high blood glucose, too much glucose, diabetic really, or type 2 diabetic, in which case you have saturated your hemoglobin A1C with more than the necessary amount of glucose. It actually binds to that protein and it becomes glycosylated and can be measured in a test called hemoglobin A1C. So if you're down around a 5.0 value, you're looking good. If you're up in double digits or above, you're looking not so good. Somebody might identify you as a pre or a true diabetic. Okay, then moving right along, here we are, and we're looking at the initial phase of lipid oxidation. So what I've done here is they've indicated here's a lipid or a triglyceride, and I drew one for you. Here's the 3 carbons. Here's the oxygens right here. This would be This would actually be an alcohol. This would be glycerol. You've probably seen that on the label of all your hand creams and lotions and stuff. And then at each of these points right here, if you were to add a organic fat, or I'm sorry, organic acid with a carbon tail, you would have something called a fatty acid. Here I drew one all the way out. Okay, so here's my first carbon called the alpha carbon. Here's my second carbon called the beta carbon. Okay, if I go all the way to the end, we identify this conventionally as the omega carbon. That's the last carbon. Count back 3, 1, 2, 3. You find a double bond with resonance. That's an omega-3 fatty acid, just the way you like it. If you have to go all the way back to 6 before you get your double bond, that's an omega-6. Okay, now you know all of the little details of omega-3, omega-6. So right here, we're going to take a little cut right there, and we're going to take this acetyl group right here, and it's going to come down, and it's going to become acetyl-CoA. That's how we do beta oxidation. And that's really all you need to know. The reason, these are like big logs, and you can just take them 2 carbons at a time and feed them into the acetyl-CoA. Use a little bit of sugar to give you oxaloacetate, and you can like spin this Krebs cycle like crazy and run all day long if you want. Some people do that. They run 24 hours. I had a friend who ran 100 miles in 24 hours. Pretty insane. So here we have the metabolism of triglycerides. I'll let you look at that yourself. And ultimately, you're pretty much operating the Krebs cycle. That's what fats do when you metabolize them. They are otherwise used for making other molecules, in some cases, fat-soluble other molecules. And in some cases, they make steroids and so on and so forth. They also make unit membrane. Remember that if you had a phosphate, if we were to take this triglyceride, take a carbon, a fatty acid off, and just to this you add a phosphate head, and keep these 2 carbon fatty acid tails rather, then you have a phospholipid, and you get to make membrane for your 40 or 50 trillion cells. So that's another need then for all of that. Here we have transamination. It's a lot of work. Your body has to work. If you have excess protein in the diet, then there's the unfortunate situation where you have to actually take the amino acid off the amino group off the amino acid in order to use it as a as energy, as an energy molecule. Okay. Then we get over here, and here we have the interconversions of carbohydrates, fats, and proteins. Okay. And what the ultimate thing here is basically that we can use proteins, we can use preferably some carbohydrates, and also preferably some fats to produce acetyl-CoA. And I've reiterated here some of the things that are common. So B1 and pantothenic acid is over there, biotin is over here. B12 actually plays a role in the production of DNA. B9, B6, and biotin are over here. Vitamin C is over here. Magnesium is over here. So you know all about that. Then over here we have the activities of insulin. So when the blood glucose is high because we just ate a meal, then the beta cells of the islet of Langerhans begins to secrete insulin into the blood, and this is actually the procedure and the mechanism for opening up the cells so that the nutrients that are in the blood go into the cells. No insulin, the cells cannot see the glucose or other nutrients. So insulin is an absolute requirement. People who have no insulin because they're diabetic, type 1 or 2, whichever one, the lack of insulin means that the cells will starve even when the blood is rich in nutrients. So that's something that we have to take a look at. Okay? So that's that page right there on page 932 where we'll end this particular spot.